Okay, so thank you and welcome to this session. As you know, the development of AI is intrinsically related to the development of hardware. And at the beginning, AI has been fueled by the development of hardware with the use of GPU and cloud computing infrastructure. But AI is booming, and there is a need for more computation and at larger scale. So consequently, in order to deploy and to develop AI, it's very crucial to develop and design specific hardware in order to accelerate the transformation. So AI nowadays influences the hardware at both the level of chips, but also from the framework program. So current solutions need to address issues of computing power, consumption of energy. They can be very expensive, and they also need to tackle everybody like to avoid many data centers and so on. So today we are very lucky because we have a panel of different actors who are involved in a solution dedicated to hardware for AI and deep learning. So I'm very happy to have first maybe Julien Demouth, who is a senior manager at Nvidia. He's working in the GPU architecture division, and he's working on deep learning, and he design and use GPU for deep learning. Then we have Ludovic Larzul, who has a long experience in building a specific dedicated supercomputer, and he has created startups, and he is actually the CEO and co-founder of Mipsology, which is a startup based on FPGA, so a promising solution, but known to be very complicated to use. So he's going to explain what he has as a solution. And then we have two more exotic players in the game, we can say that. So first we have Damien Querlioz, who is from academia. He is working at the Université of Josse in a nanotechnology center. He has a brilliant academic career because he just got a grant and an award, very famous. And he's working on nano memory in order to allow efficient energy chips. And his particularity is that he is working for bio-inspired computing, and he gets inspiration from neuroscience. And then we have Igor Carron. So Igor Carron is a CEO and co-founder of LightOn, and the particularity of this startup is to use the light properties in order to compute, and it's an hardware solution dedicated specifically to machine learning and AI. So welcome and thank you for being here. I'm very happy. And so first, I guess that I will let you present your approach and tell a few words about the pros and cons of your approach.
Okay. Good afternoon, everybody. And yeah, where should I start? If you're doing deep learning, if you are using deep learning for artificial intelligence, I'm pretty sure you're using GPUs and to train your networks or to execute your networks to infer from these networks. And so Nvidia has been working on GPUs for decades. We, at the very beginning, started to develop this technology more for a gaming environment where these GPUs were really hardware to draw images on screens and let gamers play their favorite games. But something like 5 years ago, some people realized that GPUs could also be used to drive computing power and to increase the computing power. And that was one of the components of this big boom of deep learning. Other components are the availability of more data and the existence of these smart algorithms like convolutional neural nets and all those algorithms that you probably know already. So at Nvidia, we really work on our hardware to make it as efficient as possible, but also as versatile as possible, because we truly believe that the flexibility of our hardware, the fact that you can program our hardware, is a very, very important thing for artificial intelligence. I mean, if you take a look at the research papers, you have new ideas, new algorithms coming every day or every weeks, and the possibility to implement something quickly using a well-established platform like our programming platform on our GPUs named CUDA is very key to the success of your approaches, in our opinion. So I'm probably not going to talk forever and let others talk. Otherwise, they're going to interrupt me, and that's going to be a problem. So I guess.
Okay. So Ludovic?
Hi, everybody. So I'm CEO of Mipsology. We are betting on the different hardware than Nvidia, an FPGA. So for those who don't know what is an FPGA, it's basically it's a circuit that is programmable, but at the hardware level. CPU is a set of instructions, GPU is massively parallel, but the FPGA is even more parallel. And the big difference is that you have a lot of small blocks. You can do calculation, and then you can program the circuit to have the behavior you want after you have installed the circuit in data center. Those components are available for very long, I would say 30 years. You're using them not knowing it every day. They are in every base station for your mobile. They are used in Cisco routers, but they are very professional and they are very hard to use. So what we do is basically we are hiding this hardware, forget there is an FPGA, and we allow you to use the FPGA to do the computation you would do on a CPU or GPU, but using this component. And what the advantage is compared to CPU or GPU is that because we can reprogram the hardware after the silicon was founded, we can specialize it to compute different neural network more efficiently than they would on a GPU or CPU. This is not easy, and probably nobody in this room has the knowledge and the expertise to do that. And that's what we do. We make it completely transparent for you. If you look at a little bit at the history and the future, Nvidia has done a very good job, told him already. They did a very good job because they offered the AI, the first hardware that is efficient to make the progress. But when you look at the future and what is the next step, most likely we will go away from something so generic than as a GPU to something which offers more computing and a more efficient computing.
It's very promising.
Okay, so thank you. So as has been said, I work in academia, and so I do exotic stuff that kind of works, but I think very important. So my research question is really to kind of design electronic systems that would do artificial intelligence with really the minimum energy consumption, using as little energy as possible. And I believe that really the biggest source of energy consumption in current electronic systems for this kind of application is really the fact that they separate the memory and the processors. And the fact that you really need all the time to exchange data and parameters, it really is a source of massive energy consumption. And there are two reasons for this. There are really technology reasons. You cannot actually put memory and processor on the same chip with a lot of memory. And also conceptual reason. And so in my lab, we work on both. Because actually, in microelectronics right now, the first problem, the technology problem, is currently being solved. Soon it will be possible to really have on the same chip really tiny pieces of processors, tiny pieces of memories, all embedded together. And so that's really big opportunity for microelectronics. And also on the conceptual side, so we work on solutions where you can actually have your processing, your computing, and your memory very close to each other. And for this, our inspiration is really the brain. Because the brain does not have this separation between processor and memory at all. In the brain, the memory is really all over the place, all over where it needs to be. So that's really the source of all our academic studies. So that I think very exciting because it has potential for really reduced energy consumption. But the drawback that For now, I have to admit, it doesn't really work. We have demonstrators, but not full products like these guys.
Does it work? Yeah, I guess. My name is Igor. Hi, everybody. My name is Igor Carron from LightOn. We're building a technology that is a little bit different. Unlike my previous, the previous speaker, we're exotic, but it works. And so that would be kind of a difference. Let's make sure that we have deltas between each and every one of us. We're using light to do computations, and we're allowing light to go through some diffuse media to do an operation that is at the very important in machine learning and AI. And we think that somehow using the right components and components that are not really that expensive already, we have a way to build up something that is very unique in terms of technology and tries to answer some of the issues that we're seeing in AI. That is, we have Nvidia, we have FPGAs, we have things that are exotic but not working, and but
so
really,
far from working.
But really, the issue at some point in time is going to be the fact that the data itself is getting very large, even for each and every one of you. We could take the example of, say, DNA sequencing, for instance. You already have sensors that can do DNA for you on your laptop. It's made out of England. It works well. You can do your genome in about 4 days. You don't need much power to do that. But you're going to be putting all this genome on your laptop, and you're going to need to figure out if your genome changes every day, every minutes, not so far in the future. And we're talking about very large data just for yourself or for your family. And aside from the privacy issues, we're talking about, at some point in time, doing some of these computations closer to where you're getting the data. And when you have a lot of data, nowadays, the solutions that are essentially being sold and doing very well, as you can see if you're looking at the market cap of Nvidia, is to buy a very interesting graphics cards and do those computations. We think that in the future, we're going to need to have that technology for many more people. And that means really that we need to have a technology breakthrough along the lines of the ones we're creating at LightOn, where we can do those computations closer to the sensors and to the laptops.
So thank you. So I guess that I would like to ask you what gain and what can you expect in terms of gaining performance, in terms of computational cost, as well as economical cost. So what are you expecting?
Okay. So I think I want to mention a couple of things that were said before. One of the things that was said is that we have to be thinking more about the size of the data and where we put the data. And actually, if we want to increase our computing power, we have to ask ourselves, and all of us, not only the guys building the GPUs or building the FPGAs or whatever, how much information our data contain and to what level of numerical precision we can go to improve reduce the size of the data and still deliver the correct answer. And this is a big trend in the industry these days. We're trying to reduce the number of bits we need in our data to keep the results, but improve the efficiency of all our systems. And that's one big thing we're trying to achieve. And that's very important for the future. And it's not only us building the hardware, it's all of us. Think about how much information you have in your data, how many bits you need, and you probably need way fewer bits than you're using today. And if you think in those terms, you're going to have better performance. Regarding the economical cost, I mean, judging by the number of GPUs we're selling, it's probably much cheaper than what we had before. And definitely, when you increase the compute power, reduce the size that it takes in your data center, you're gaining a lot of money, and that's the reason why people buy GPUs, because if you need 5 GPUs to do the same work as many more CPUs, then buy your 5 GPUs. Doesn't matter how much a GPU costs. At the end of the day, you're gonna earn money, and probably well do so.
So I'm going to start. I agree with him. He's a great guy. He's doing advertisement for me, which is even better. One of the strengths of the FPGA is that indeed we can go to the bit level. We can decide that after the circuit was built, so we have this advantage that without killing the accuracy, we can reduce the precision of calculation, and that's indeed where the industry is going in terms of deployment. There is one thing which is the training and one thing which is the inference. When you look at the inference, the problematic is how much data you're going to process per day. When you're talking to people like Amazon, Apple, Samsung, Google, Microsoft, they're not looking at the training data set that you can process every day. They are looking at billions of images, billions of voice pieces. They are looking at number of data which are crazy. And when you want to build a data center to process that, it's not the same problem as putting 5 GPUs in a corner. And that's where I think in terms of processing trends, we need to find one order of magnitude higher than GPU in the next few years and another one in the next few years after that to allow you to build even more complex model and solve more complex problems. So that's where we are going with FPGA, basically. We want to have that kind of acceleration, reducing the power, which is another problem for data center. We are using too much power. I'm sorry, GPU are not a good example. And the cost comes after that for me. Number of watts, what power of calculation we can use, and reducing the power used in terms of electricity and cooling.
So what I promised in my project is that is that actually with our ideas we could reduce 1,000 times the energy consumptions with regards to current GPUs. And actually that was reasonable. I mean, I think this was really justified. Actually, at the end of my project, I don't know, because some of the ideas that were really academic and some that are the source of our low energy consumption, well, now you are doing it in GPUs too. In particular, the reduced precision. It's very, it used to be very academic idea. It's very brain inspired. I mean, synapses in the brain are not 32 bits floating point, definitely not. And actually, it's nice to see more the products taking the same direction. On the other hand, I usually make no promise on speed, because very often all our ideas really help with the energy consumption, but typically do not help at all for the speed. So on this, I promise nothing.
Benchmarks are kind of an interesting exercise when you're trying to compare different technologies that are not really that close to each other and everything. So we have our numbers, and they're pretty impressive, really, compared to the type of operations that you could do on either a CPU or GPU. And it has mostly to do with the fact that we have somehow solved the problems that Damien was talking about, which is really having access to the memory right there, as opposed to expecting that memory to do some traveling from wherever it is to the computational node. So we have somehow solved that problem, and to a certain extent, that allows us to go much faster than what we can see in electronics. I'm not going to go into numbers yet. Maybe tomorrow at the startup pitch, you might see some of these numbers. But we're doing one operation right now, and we're thinking about doing additional operations so that eventually, I think the other speakers are essentially trying to point out the fact that the hardware is kind of, well, catching up to what the algorithm folks are doing these days. And the algorithms are changing, like what Julien was saying, like every day. And the catching up for the hardware is extremely hard, mostly because they are not accustomed to those loop cycles of a day or week type things. And whenever we're trying to do something better when it comes to classification and so forth, we get to see people coming up with larger algorithms to do better things and higher things to the level of AI as opposed to the lowest levels of recognition type of thing. So we're at the hardware level, we get to be very sensitive to the fact that those algorithms are themselves very much moving and changing, and it's kind of a target that changes over time. We think at LightOn we can actually answer some of these issues pretty well, but everybody else, like at LightOn, we have these difficult issues of trying to catch up with the algorithm race that is currently going on right now.
So thank you very much. So unfortunately, we need to stop. So I would like to thank you very much for showing us how our hardware is really important for developing IA. So thank you.
Thank you.